Now we're going to solve a problem that is quite nice because it makes a connection with pretty much everything that we've discussed so far in the course. And we're therefore going to combine stress-strain relation, stress transformations, principal stresses, and therefore eventually strains, and so on, the concept of isotropy, and pretty much what we've mentioned, limited amount of mentioning about failure is going to sort of, as a motivation at least, is going to come in. Failure is a concern of our next topic, but it's been motivating in everything that we've done, because the motivation as well, why are we looking at the searching for the maximum value as well? Because eventually we're wondering whether the material will fail or not. Okay, so now remember the discussion of failure with respect to stress. That's how we characterize failure. It is based on a given state of stress. But for that, I need to know what the original picture of the stress is. I need to know the stress components. But often you cannot measure the stress directly, but rather only indirectly through the measurement of strain. And the measurement of strain is something that can be sometimes a lot more practical. And there are tools for doing so. And one tool is a tool called strain gauge. So a strain gauge is something, here I have a structure, a metallic structure, on which we have strain gauges. And these strain gauges, if you can see, in fact, in this structure there are multiple ones. Here, perhaps there is one that you can see a little bit more clearly. So a strain gauge is a tiny device through which we have wires. We will run a current, and there is a tiny wire that's wound up here. And eventually, when the electricity runs through it, if the voltage is constant, you measure a current, or if the current is constant, you measure a voltage, and they're proportional to each other through the resistance of the overall structure of this wire. And we know from our basic physics that if a wire is strained, if you elongate it, if you change its length, its resistance changes. And therefore, this tiny setup, when it's stuck to the underlying material, so when the material deforms, this is not stiff at all, it will just pick the deformation of the underlying material, so it will deform with the local metallic deformation. It will be subjected to the same strains. We can measure that strain by monitoring its resistance. If we have a calibration of the amount of change in the resistance to the amount of strain, just in a professional manner once, then for all remaining deformations I will be able to measure the strain directly. Okay, so that's the idea of a so-called strain gauge. This quantity, this device here is called a strain gauge, and you can put several one of them at various locations throughout a structure to monitor the state of strain at a, for instance, point where you expect some stress concentration, etc. Now, one thing to notice is that the strain gauge always has a certain axis. So what the strain gauge measures, again back to the scenario, what the strain gauge is measuring is the strain, which is first of all normal, and the direction of that normal strain is along that direction. So it's measuring a normal strain in a specific direction, or if you like, strain on a plane with normal this direction. Okay, so that's the direction of the normal strain, and the plane that's associated with that normal is this normal. Now, if you orient this strain gauge in some arbitrary direction, then you would be measuring the normal strain on the plane with that orientation, right? So it allows you to measure a normal strain in any direction that you wish to. All right, so that's the concept of a strain gauge. So, and the final thing to notice here is that usually you put the strain gauge, you don't have to, but you put the strain gauge usually on a free surface. And remember what a free surface means. It's a surface with a certain normal, and there is no normal stress, there is no shear stress in either direction. So it is sort of a plane stress scenario. This thing will be loaded within the plane of this beam, but not in a direction that's perpendicular to it. So no shear or normal stress is associated with that direction. So it's a state of plane stress, and the plane that we're talking about is the plane of this beam. Okay, so now having motivated our idea, then we will go ahead with an example. So strain gauge, you'll see it's not employed always by itself, but for a very clear reason. Usually, for instance, you can do so in combinations of 3. Now, 3 is a special value that we're going to see how it arises. Now, eventually, when we're going to put 3 strain gauges, we will put them at a certain orientation. And let's pick, for the purposes of our present example, 3 strain gauges that are oriented as such. Now, we want to eventually, why are we measuring the strain? To ultimately, you'll see, determine the stress at a point in the structure, and that's this point. And I want to decide, ultimately, if the state of stress is such that at this point there could possibly be failure along some plane, along a principal normal or shear stress plane that I can eventually determine with the analysis methods that I've developed. So I'm interested in the state of stress at a point, and to calculate that, I want to measure the state of strain. So you better put your strain gauges as close as possible to that point. I'm going to exaggerate and put them far away. Now, I'm marking the direction of the strain gauge like this with a line. So those are my strain gauges. In this case, I have 3 strain gauges, A, B, and C, let's call them. Remember, each one delivers a measurement which is a normal strain along its corresponding direction. So I know they're not in the same direction, it would be useless, and they're in different directions. Let's say that they are oriented at angles of 60 and 120 degrees. Okay. All right. So now this orientation set of 3 strain gauge orientations, it's not also unique. I could have picked them to be in such a way that they're oriented, let's say, like this, where these are perpendicular, and then there is yet a third one which is oriented at an angle of 45 degrees. So this would be an alternative choice of 3 strain gauges. Either way, it will be sufficient. What's important is I have 3, and they work in a special manner, the way they are oriented to deliver me the information that I need. Either way, this combination of 3 is typically called a strain gauge. Rosette. Okay, so you don't have a single strain gauge, but you have a rosette of them, and together they will help me characterize the state of strain at a point in the structure towards the assessment of safe failure. And I need to know, of course, something about the material behavior. I know, for instance, that this material is isotropic. And the linear elasticity constants are 200 GPa and 0.3. Okay, so it's steel. Eventually, if I need the shear modulus, I always keep in mind it doesn't have to be separately provided. I can calculate it as such, and that's going to be about 76.9 MPa in this case. Good. Now, the question is going to be the following. At a point in the structure, on a free surface, let me emphasize that, so it's going to be a free surface. And so a free surface is going to be a plane stress. Plane stress and the perpendicular direction of the plane is going to be a certain direction that I need to explicitly indicate eventually, but let's just note that for now. And so on a free surface, you put a strain gauge. It is apparently a steel beam or steel structure. Could be a complicated structure, could be on a wing of an airplane, and eventually you're measuring the state of strain. It is a plane stress scenario, so I remember, keep in mind, it's not necessarily, it is not in fact in general a state of plane strain unless Poisson ratio is 0, which is not, and therefore it's going to be a state of generalized plane strain. And the question is, well, suppose I measure the normal strains epsilon A. The strain gauge A delivers a measurement of 190 micro strains. This is one way to denote it. I could write 190 times 10 to the minus 6, right? Here, remember it's not microns. That would really mean that it's a micrometer. strain is dimensionless, so 190 microstrains probably is maybe one way to write it, or simply 190 10 to the minus 6. Epsilon b is going to be 200 microstrains, and epsilon c is going to deliver, that strain gauge is going to deliver a reading of 300 microstrains. Okay? And now the question is, well, for this material, find out eventually what the principal strains are. Find the absolute maximum shear strain, and we find that through the principal shear strains, of course, and eventually also find the principal normal stresses as well as the absolute maximum shear stress, which is found through the principal shear stresses. Okay? And eventually the orientations that are associated with all of this. It would be sufficient to know only one. We know that we have a generalized plane stress and a generalized plane strain, so there would probably be one angle associated with this. That would be sufficient. Let me call that theta, and only the angle associated with the rotation from the original picture to the principal stress picture. That angle is the same as the principal strain picture, because remember, principal directions are the same. I've stated without proof. So if I provide all of this information, I will be done. So it's quite a lot of information that I need to provide. And it turns out there are two ways to solve this problem. Let me proceed with one way, and then we'll talk about the other one. So first, I will try to calculate the strain components, principal strains, and then from the principal strain information, I will go to principal stresses, etc. Okay, so now, but to find the principal strains, and this way I will be able to demonstrate some of the ideas that we mentioned just in a lot of words, I need to find the state of strain. So I need to find epsilon x, y, z, etc. But I'm not given those. I'm only given 3 strain gauge measurement readings. So the first thing I need to do is pick a set of axes. That's really up to you. I could call this x and that direction y, or I could call this z, x, perpendicular direction, something else, y, etc. But eventually what I will do is pick something simple. I'm going to pick this direction to be the x direction, and that direction to be the y direction, and the out of plane direction is going to be the z direction. Okay, so that's nice. Now then, let me go ahead and mention a few things. Now, first of all, what we know is from my earlier discussion in words, what I know is that if I am given a certain state of stress that is described through epsilon x, epsilon y, epsilon z, and gamma xy. Okay, so let's put that as well. This is a state of generalized plane strain, which is what I expect in this scenario. And if I know epsilon xy and gamma xy, then I can write the value of any epsilon, any normal strain, as a function of theta. And I told you that because the mathematics is the same, it's going to work exactly as it did for the equation for sigma x prime. And that equation for sigma x prime was equal to sigma x plus sigma y, in this case epsilon x plus epsilon y over 2, plus sigma x minus sigma y, so in this case epsilon x minus epsilon y over 2. Okay, so it works exactly in the same way. The mathematics is the same, except when you have a tau, so here I would have a tau xy sine 2 theta. Now I'm going to write gamma xy, and I emphasize with a factor of 2. Okay, so that is now the relation that I have for any angle change theta that will deliver me a new value for the normal strain. So now I don't know epsilon xy and gamma xy really at first sight, but I have a lot of normal strain measurements along different directions. So first of all, I have epsilon a, and I notice that epsilon a is really equal to simply epsilon x prime at theta equals 0. And if you plug in theta equals 0, no surprise, the result is epsilon x, okay, because I'm measuring the normal strain along x. Okay, so that was easy. I know that epsilon x is equal to 190 times 10 to the minus 6. Good. Well, then I have epsilon b, which is equal to epsilon x prime at 60 degrees. Okay, so you can go ahead and plug that in there. Epsilon x plus epsilon y over 2 plus epsilon x minus epsilon y over 2. And now notice, actually, why don't we go ahead and plug in epsilon x in there and pick our units to be microns with the understanding that we do everything consistently. Okay, so 190 microns. So this value here is 190. This is also 190. Cosine of 2 theta, which is 120 degrees, plus gamma xy, which is unknown, over 2, remember, sine of 120 degrees. And epsilon c is just epsilon x prime oriented at an angle of 120 degrees, which is again 190 plus epsilon y over 2 plus 190 minus epsilon y over 2, cosine of 240 degrees plus gamma xy over 2, sine of 240 degrees. Okay, so I already know epsilon x. I use it in these equations, and I ended up with results which tell me that so these two can be solved for epsilon y and gamma xy, because I know epsilon b is 200 and I know epsilon c is minus 300. So these together will deliver me the result that epsilon y is equal to minus 130 microstrains and gamma xy is equal to 577. Okay, and that is what I meant with the equations applying in exactly the same way. Now, the next step, now that I know the shear strains, the normal and shear strains with respect to x and y, so now I can go to the question of what the principal strains are. And to answer that question now, I will use the Mohr circle because I have a state of generalized plane strain. Now, at this point, you might immediately ask yourself, well, what is epsilon 3? Well, epsilon 3 is equal to epsilon z, and I've already told you that it can be calculated, and do that on your own once again through the relations that we have that I have provided to you. And that relation says that epsilon z is simply minus nu over 1 minus nu epsilon x plus epsilon y. Okay, so if you go ahead and calculate that, we would obtain epsilon x, which is 190, plus epsilon y, which is 130 but negative. Okay, and then we multiply it with 0.3 divided by 0.7, and we would obtain a negative 25.71 microstrains. Again, goes without saying. Okay, so I know the third value of the shear strain. Remember, gamma zy and gamma zx are both 0 because it's a state of generalized plane strain. Why? Because of the fact that we have a free surface. Okay. Now that we have all of that information, let's go ahead, draw the Mohr circle. So the Mohr circle is going to be drawn, remember, in exactly the same way, except that I have to keep in mind how the axes are labeled. So the horizontal axis is going to be the normal strain. This one is going to be the shear strain, remember, divided by 2, because that's the correct interpretation of the shear strain. So that factor of 2 is there as well. And so now I'm going to go ahead and put in the correct values of the points. So I will obviously have an x point for the strain, an x point, which is exactly as before. So it's going to be epsilon x minus gamma xy half. And the y point is going to be epsilon y plus gamma xy, but don't forget the half. Okay? So I again assume that everything here is in terms of microstrains. So the values which I have are equal to epsilon x, which is 190, minus half of that shear strain value, which is minus 288.5. And here I'm going to have minus 130 and minus plus 288.5, okay, because it goes with a plus. So then I go ahead and put those points on my map. So perhaps not to very good scale, but one of these points, let's say, goes there. The other point goes over here, okay? So this is the x point. Let me continue after a tiny glitch. I was plotting the x point, which is 190 minus 288.5, and I plotted here as well the y point, minus 130, 288.5, and then we go ahead and draw the dial. And the intersection, the center of the circle I'm about to draw, it's at minus 130 plus 190, 60 divided by 230. So you see, all the calculations are exactly the same way as we did for the stress Mohr circle. And so let me go ahead and draw the circle now. That is the circle that is associated with the xy plane. Okay, so that is going to eventually, the center is A, the radius is going to be associated with that distance. So that's, right, I can easily calculate. So it is 190 minus 30, so that's 160 squared, plus 288.5 squared, square root, so the radius is approximately 330. Microstrains, right? Okay, so that is going to send me from here to a, first of all, x will rotate through an angle 2 theta n on the Mohr circle, theta n on the physical space. You can easily calculate, in this case, 2 theta n to be 29 approximately, or theta n to be roughly 14.5 degrees. Then we can go ahead and calculate also the principal stresses, which is epsilon 1 equals 30 plus 330, which is 360, or 30 minus that value, which is negative 300 for the second principal normal strain, epsilon 2. Great. So now of course, I can at this point immediately go and calculate the largest shear strain I obtain within the rotations that lie in the xy plane, or about the z-axis, and that would deliver me a value here that is equal to the radius 330 for gamma, so that's 1, 2, that would be gamma 3 half is equal to 330, or gamma 2 is 660 microstrain without explicitly saying so. Okay, so that is the value of gamma 2. But is that the largest one? I have to always ask myself, well, that's where the third strain comes in. Well, the third strain in this case is minus 25.71. So it's going to go, if this is 300, it's going to be just less than 1/10 of that. So that's where epsilon 3 goes, which is equal to epsilon z, which is minus 25.71. It's quite small, and the circles associated with that are not going to be any more critical. So this value of gamma is actually simultaneously the absolute maximum shear strain. So now the question is, remaining questions are, well, what are the principal normal stresses and what is the absolute maximum shear stress? So first of all, the absolute maximum shear stress is something that I can immediately determine from what I've done so far. So I know the value of G, and therefore tau max is the easiest ones among all. It is equal to simply G times gamma max, and if you calculate that, you will find a value which is about equal to 50.77 MPa. Again, goes without saying here, all the units are MPa for stress. Now, well, that takes care of that one. Similarly, I could have solved multiplying gamma 3 with G would give me tau 3 and so on for the remaining shear stresses, but here in this case, I was able to directly solve for tau max like that. In general, of course, if you go from the stress state to the principal picture, you calculate these, choose the largest one, but here, that's what I've done. Okay, so then the remaining question is, well, what are the principal stresses? Well, to calculate the principal stresses now, what I have to keep in mind is what I've said before. Well, the relation between stress and strain holds in the same fashion for all types of choices of coordinate direction. So in particular, I can choose the principal direction, and with respect to that direction, I'm going to have the stress in the corresponding direction minus nu times the stress in the remaining directions, which is nu sigma 2 plus sigma 3. But it's a state of plane stress, and therefore I will also remember that sigma 3 is actually equal to sigma z equals 0. Because it's a state of plane stress. And epsilon 2 is equal to 1 over e sigma 2 minus nu sigma 2, sigma 1 plus sigma 3, sorry. And here as well, sigma 3 is equal to 0. Now, of course, there is a third relation. Epsilon 3 equals 1 over e sigma 3 minus nu sigma 1 plus sigma 2. But that relation has already actually been implicitly employed here. So if you set sigma 3 equals 0 and plug in the expressions for sigma 1 and sigma 2 that you find from there into that expression, what you will eventually find is exactly a result that is equivalent to this one. In other words, so for a state of generalized, for a state of plane stress, you have a generalized plane stress scenario where in terms of epsilon x and y, this is the value of epsilon z. So epsilon z is equal to epsilon 3, so we're not going to have any new knowledge emanating from that final equation. So these two equations are all that we need presently. We've already made implicitly use of that one. And therefore, I know the value of epsilon 1. We found it. It is equal to 360. Now the units are important. This is 360 microstrains. This is equal to minus 300 microstrains. E is going to be equal to 200 GPa. And so you can go ahead and eventually find the values of the stresses, and sigma 1, from these two, you will find that sigma 1 is equal to 59.34 MPa. Again, goes without saying it's MPa, and the sigma 2, the second principal normal stress, is minus 42.2 MPa. Okay, sigma 3 is equal to 0. Again, I encourage you to derive these relations that I've written on the previous slide as well, and also solve these equations explicitly. Similarly, solve these in terms of these values to complete the whole example. Now, that is one way to solve this example. Certainly, I've answered everything that was needed. There is yet another way to solve this example, but notice that the procedure that I've followed is already demonstrative of the idea of working with strains towards principal values. And the idea is exactly the same as for stresses, except for that factor of 2 that we must remember. And ultimately, we have also brought together many concepts that we discussed before, like relation between stress and strain. Remember again, why are we doing all of this? Why is this a nice example? Because we want to know at a surface of a structure, because let's say we suspect that it's a critical point, whether the stresses are close to being close to delivering failure or not, or whether to within a safety factor I am safe. And so I want to calculate the, say, if the material is sensitive to that value, the absolute maximum shear stress. Well, to do that, I do a strain measurement, and you see, based on the equations that I have access to, I can calculate the state of stress with respect to XYZ axis. I can convert that picture to the principal picture and go for, say, the maximum shear strain, and thereby extract the information that I need. The information that I needed might have been the maximum normal stress and not the shear stress. In that case, I can extract that information as well and use that towards material failure, which we're ultimately going to do in the next topic. So that's why this is a nice example that takes us all the way through what we've done so far in the course and connects many concepts together.